Back in 2012, astronaut Chris Hadfield was getting ready to blast off to the International Space Station. Before he did, though, he got on Reddit to host an Ask Me Anything, where users of the social news site could ask Chris all of their most burning questions. And during the Q&A, Chris described what it's like to blast off. Launch is immensely powerful, he said, and you can truly feel yourself in the center of it, like riding an enormous wave, or being pushed and lifted by a huge hand, or shaken in the jaws of a gigantic dog. The weight of over 4 Gs for many minutes is oppressive, until suddenly, after 9 minutes, the engines shut off and you are instantly weightless. Magic. Today on Stereochemistry, we'll be talking about that magic, or the chemistry behind the magic, I should say. Specifically, the chemistry of rocket fuel. And I've got the perfect co-pilot here to propel our journey. Hi, Sam.
Hey, Carrie.
So, Sam, the idea for this episode came from you. What got you interested in rocket chemistry?
Well, a lot of the space stories I write rely on rockets. Rovers wouldn't be roving on Mars, telescopes like Hubble wouldn't be exploring the universe if rockets hadn't put them there. So what I'd like to say is that I developed a deep respect for these workhorses and the unsung chemistry that makes them work. But the truth is, I read a really smart and fun book about rocket chemistry, and I wanted to dig in and learn more.
And what is this book you speak of?
It's called Ignition, with an exclamation point. It was first published in the early 70s and written by rocket chemist John Clark, who was also a sci-fi author who palled around with people like Isaac Asimov. Clark's accounts of rocket research are completely captivating. The book was out of print for a while, although there were excerpts circulating on the internet, which is where I first found it. Anyway, it's back now, and if you want to learn more about the heyday of American propellant chemistry than we could include here, you should definitely go check it out. Clark died in 1988, so unfortunately I couldn't talk with him, but I did the next best thing. I talked to some of the other rocket chemists who were there at the beginning. Well, the beginning of modern rocket science.
Oh, cool. So how do you define modern rocket science, and when did it start?
Modern rocketry is basically what let humans escape Earth's gravity for the first time, and it started in the late 1800s.
Okay, but unless you have a Ouija board you're not telling me about, I'm guessing the scientists you talked to would have been active a bit later than that. So when did they come in? And big picture, what did they tell you?
Yeah, you're right. The most seasoned people I talked to did their work in the 1950s and 60s. That was a really wild, unique period when almost unlimited funding for rocket chemistry was available. Unfettered by budgets and in some cases by what you might think of as common sense, rocket scientists during that era pursued some truly wild chemistry looking for better propellants. What was fascinating to me is that even though the scientists during that time made a lot of really important discoveries, very few of those molecules ended up being used in working rockets. Instead, those important discoveries have transformed multiple fields of chemistry.
But we're still going to talk about the rockets though, right?
We'll definitely talk about rocket chemistry. Unfortunately, there aren't that many scientists still living from the early part of that heavily funded era. But the ones still with us have some amazing stories. As you might expect, there were accidents, and they tested some fascinating substances. But what I also learned is that rocket chemistry isn't a done deal. It seems like a second stage of rocket research is now taking place, with scientists in the US, China, and elsewhere pushing into new areas of chemical space.
Before we get into all of that, though, let's start with the basics. What exactly is rocket fuel, and how does it work?
Okay, so Chinese inventors made the first rockets in the 13th century, powered by gunpowder. But remember when I said modern rocket chemistry started in the late 1800s? That was thanks to Russian scientist Konstantin Tsiolkovsky. In 1896, he published a paper titled Exploration of Cosmic Space by Means of Reaction Devices, meaning chemical rockets. In it, Tsiolkovsky showed mathematically that gunpowder doesn't have enough energy to put a rocket into space. He proposed instead reacting liquid oxygen and liquid hydrogen as a propellant.
Oxygen and hydrogen, why those two?
Well, any propellant is going to need two basic components, a fuel and an oxidizer. In Tsiolkovsky's proposal, the hydrogen is the fuel and the oxygen is the oxidizer. They react by combusting. Now, you can think of a really basic rocket as a chamber that controls the geometry of the reaction. As the reactants combust, the rocket shoots hot gas, the reaction product, out in one direction. That produces a force that pushes the rocket in the opposite direction. That's Newton's third law for you physics nerds. Now, back to Tsiolkovsky. He came up with an equation that can tell you if your rocket will make it to space. To be fair, other scientists also independently derived the same formula to describe propulsion, but scientists call it the Tsiolkovsky rocket equation because he was the one thinking explicitly about rockets going into orbit and beyond. And what that equation tells you is that if you want to escape gravity, you want a chemical reaction that runs hot and generates low-weight products. High temperature means reactions that release a lot of energy. Combustion ticks that box.
Okay, I see. And the product of the hydrogen and oxygen combustion reaction is water, which is a small molecule, low weight. But why is it important to have low molecular weight products? Wouldn't more massive molecules push the rocket harder?
Actually, no. The way several rocket scientists explained it to me is that lighter, smaller products means the exhaust can be denser, and that means more force.
Got it. So that was more than 100 years ago. What are we using now?
So remember how I told you that a lot of the propellants that chemists tested during the 50s and 60s didn't make it into rockets? Well, this past August, when the US Air Force launched a GPS satellite into orbit, they used a rocket powered by, you guessed it, liquid hydrogen and liquid oxygen.
Okay, so a century ago, a scientist proposed using hydrogen and oxygen to propel rockets into space, and we're still using those propellants? That's our shortest episode ever.
Don't worry, there's still a lot of the story left to tell. First of all, not all rockets today run on those propellants. Those scientists in the 50s and 60s did actually change rocket chemistry. To understand how rocket chemistry ended up where it started, we need to understand the things those chemists did and what happened after. I want to start with Fred Hawthorne. He might be the living person who best represents the arc of 20th century rocket chemistry. Hawthorne is the winner of a National Medal of Science and an inorganic chemistry expert. He's 91, and some people call him Mr. Boron, which you'll understand soon. He was a rocket chemist at the company Röhm and Haas when they were leaders in the propellant world. Later, he was a chemistry professor. But before all that, he was a kid with a chemistry set.
When I was about 12 years old, I got a chemistry set, a Gilbert chemistry set, and that fascinated me.
You can probably picture a Gilbert chemistry set. They came with test tubes and vials of all kinds of different chemicals, the sort of thing that could never be sold to kids today.
And I spent all my free time learning chemistry. And I was just really drawn to it.
Hang on, let me do some quick math here. If he's 91 now, that means that when he was 12, it was like, what, 1940? So this is right around the beginning of World War II.
Yeah, and the timing is important. 2 years before Fred was born, American physicist Robert H. Goddard launched the world's first liquid rocket, using liquid oxygen as an oxidizer and gasoline as a fuel. That set off a flurry of rocket research in the US, Europe, and Russia. Fast forward a few years, and the German Wernher von Braun started his rise to prominence and infamy in rocket science. He was a member of the Nazi Party. Thousands of von Braun's V-2 rockets killed civilians in Allied European cities. Thousands more died in the concentration camps that built the rockets. At the end of the war, von Braun surrendered to the Americans, who were keen to use his expertise in their own rocket program. In 1950, von Braun moved to the Army's Redstone Arsenal in Huntsville, Alabama, to lead the country's rocket program.
So this is what kicked off that unique period of rocket research in the US, when rocket scientists were just rolling in money. Where does Fred Hawthorne come in?
Right. Redstone is also where Fred ended up in 1954 after getting his PhD. He was working as a research chemist for the Röhm and Haas Chemical Company, which had its rocket labs on the Army base. The US military funded Röhm and Haas's rocket research, and it was going all out in pursuit of higher-performing rockets, because the US didn't want to get beaten by Russia into space and in the nuclear missile race.
Money was not a big problem. Time was a problem, because we were competing with the Russians. So things were rather crude and a little bit sloppy at first.
Redstone was a little frustrating for Fred as a scientist. He says there wasn't time or interest in understanding exactly what made a good propellant. People weren't really interested in the fundamental chemistry.
They simply threw a lot of things together and had a lot of troubles, and very few real successes.
But you said at the start that Fred eventually did do some fundamental research that would change chemistry, even if it didn't necessarily change rocket science.
True. Fred would eventually work with compounds called carburenes, which are caged molecules made of carbon, boron, and hydrogen. But at first, he was working with a propellant called petronacrylate. And if you're listening to this episode to hear about rockets blowing up, you'll want to hear Fred's petronacrylate story. Petronacrylate is a polymer with a hydrocarbon backbone and side chains sprouting from it that are made from esters of PETN, which is one of the molecules used in plastic explosives. And petronacrylate is a solid propellant, so it's not in a tank like liquid hydrogen or kerosene would be. It's poured into the rocket and then hardens into a rubber. Fred describes petronacrylate as a little twitchy, and the Army wanted a lot of this twitchy propellant for a test rocket, 6,000 pounds to be exact.
That's about 3 tons of stuff. That's a hell of a lot of explosive material.
Fred and other Röhm and Haas chemists and engineers managed to build the rocket, and they set it up on the test range. Because they didn't want it to actually launch, Fred says they buried it in dirt, concrete, and anything else they could put on top of it. They also wired it up with instruments to learn more about how this new propellant performed, which made the test rocket a very valuable piece of equipment. On the day of the launch, Fred and a couple dozen other people gathered on a grandstand about 300 meters from the rocket, excited to watch the test fire. The engineer who filled the rocket with propellant was sitting in front of Fred, and Fred asked how the propellant looked.
And he said, well, it's got a crack in it, but we filled the crack. It was epoxy, and that should be okay.
Fred means there was a crack in the surface of that rubber column of propellant, and as you might guess, it was not okay.
Anyway, we started counting down. 5, 4, 3, 2. And when it got down to 0, we were too far away to hear anything yet. And then we saw a shock wave coming through the grass, and it came through and hit us. So we got a pretty good ride out of that.
Despite the shockwave and supersonic rocks whizzing over the crowd, Fred says nobody was hurt. An office building about 500 feet away was destroyed, but it had been evacuated before the test. And about 50 cars in a nearby parking lot were crushed by falling concrete. Even closer to the rocket was a trailer full of equipment collecting data from the instrumented rocket. Fred says it was shot through with holes, but somehow the 2 technicians inside were unhurt, and they managed to collect the data as well. It turned out that instead of burning from the bottom up, the petronacrylate had started burning up the surfaces of that crack in the propellant. The rocket wasn't designed to handle pressures of hot gases there, thus the explosion. This wasn't the only petronacrylate mishap at Redstone, and shortly after, Roman Haas decided to abandon the molecule, which was apparently just too twitchy to pursue further.
I mean, if my research project exploded and threw a bunch of rocks and concrete at me, I'd be inclined to abandon it too. So this is when Fred switched to carburenes?
Yeah, so Roman Haas brought in a new director of chemistry research at Redstone, Warren Niederhauser. He set his chemists on 2 new lines of research. One targeted inorganic compounds, specifically boron. This was the group Fred was in charge of.
You see, boron's next to carbon in the periodic table. It ought to behave very much like carbon. There ought to be a corresponding chemistry there that is just waiting to be developed. And that was my thinking. And sure enough, it worked.
The US military had actually been investigating boron compounds as potential jet fuels because they burn about 50% hotter than hydrocarbons. But burning boron compounds also damages jet engines and produces toxic boron oxides. So Fred's group got involved in carburenes, which were discovered by another group of rocket chemists. Remember, these are caged molecules made of carbon, boron, and hydrogen. These were more stable than the original boron compounds. Fred's group figured out how to make acrylate esters of carburenes, among other compounds, and it was all slow going at first. They were testing everything in small batches, and they made their starting material, decaborane, from scratch. Decaborane has, you guessed it, 10 boron atoms in its caged structure. Just to illustrate once again how this period in rocket science was fueled by extreme amounts of research funding and a desire to compete with the Russians, let's go back to Fred. He says one day he got invited to give a talk to a group of Air Force scientists studying solid rockets.
I talked about 20 minutes, and the guy said, hold it, I'll be back. And he left the room. And he came back about 15 minutes later and said, I've just given orders for you to receive a long ton, that's 2,200 pounds, of high-grade decaborane to be delivered to Roman Haas.
Before that, Fred says his team was spending about $10 a gram on decaborane. A long ton translates to almost 100,000 grams, or $10 million worth of the stuff.
I see what you mean. Money was really flying around back then. So did their investment in Fred pay off?
Well, in some ways, yeah. One of the carburenes compounds he tested burned 10 times as fast as petronacrylate, the culprit in that spectacular test failure. And it was easier to handle, too. But it didn't end up delivering any more energy than petronacrylate in their experiments. But after Fred left Roman Haas in 1962 and went into academia, he took boron chemistry to new heights. Fred figured out how to make metallic compounds with carburane ligands, complexes that have proven useful as chiral catalysts and radioactive markers for medical imaging. He's also explored carburane derivatives that could be used to selectively target tumors with radiation therapy. Today, he's an emeritus professor at the University of Missouri. I asked him if it's fair to say that propellant chemistry is one of the reasons boron chemistry developed the way it did.
Yeah, oh yeah.
Hence the nickname Mr. Boron.
Right. It's a similar story for other rocket chemists pushing the envelope at that time. Emma Lawton was a contemporary of Fred's. Emma worked on fluorine chemistry at Rocketdyne, a rocket engine company in Southern California. He made a whole bunch of fluorine compounds, including wild molecules like chlorine pentafluoride and oxychlorine trifluoride.
What's so wild about those?
These interhalogen compounds are incredibly strong oxidizers. They're known for combusting with basically anything they touch. Chlorine trifluoride, a tetrahedral molecule made of a chlorine atom and 3 fluorines, is maybe the most reactive of the bunch. It's hypergolic, meaning it ignites on contact, with wood, cloth, and most metals, but also with sand, asbestos, and even water. But like Fred, Emil told us these fluorine compounds were dead ends, at least for rocket chemistry. I asked him if any of his molecules ever made it into rockets.
Surprisingly, none of my molecules did.
Did Emil say why not?
Emil's group never scaled up their fluorine reactions because the compounds were too reactive to be practical. He says people were initially interested in these molecules because they had high performance for their weight, which meant rockets that could carry more payload for their size. But engineers found ways to miniaturize electronics and guidance components, and those weight savings made it so that rockets didn't need the dangerous fluorine propellants. Emil was done with halogens, but he did stay in rocket chemistry, and later in his career would help the military investigate rocket accidents.
Okay, so the chemistry Fred and Emil worked on didn't end up in today's rockets, but something did. So what did end up taking off?
Well, to answer that, I have to tell you about what happened later on, after this period of lavish spending we just talked about. Rocket chemistry entered a sort of dark ages. The sense of urgency was gone, and so was the funding support.
Wow. So what happened to bring about the dark ages of rocket chemistry?
I'll tell you, but after the break. We'll hear about that plateau and where rocket chemistry went next. Stay tuned.
Hi there, this is Juliana Viglione, CNEN's editorial fellow. I hope you're enjoying this explosive episode as much as I am. We at CNN work hard to bring you the very best stories on stereochemistry, and we wanted to take this opportunity to ask for your feedback. What do you like? What can we do better? There are a bunch of ways you can let us know. If you're listening to this episode on Apple Podcasts, you can leave a review or a rating without even leaving the app. That helps other chemistry enthusiasts find this podcast, and it will help us make this show better for you and all our future listeners. And you can always email CEN_multimedia@acs.org. Have an idea for a chemistry story you'd like to hear? Let us know. Thanks to everyone who has rated stereochemistry already. Your support means a lot to us, and we are excited to bring you even more captivating stories from the world of chemistry in the coming months. And now, back to the show.
I'm on the edge of my seat here, Sam. What happened to put the brakes on rocket chemistry?
The scientists I talked to had a lot of ideas about why rocket chemistry research lost some speed. Money and politics definitely played a role. Rocket scientists in the 50s and 60s were awash in government cash and racing with the Soviets to build rockets that could reach the moon or deliver nuclear warheads across the globe. After the moon was in reach and the Vietnam War sapped America's interest in military adventurism and the Cold War was growing stale, the political will and financial support for exotic chemistry research started to dry up.
So the funds are gone, political support has tanked. How did rocket research continue? I mean, it didn't stop completely, right?
No, it didn't stop, but it was definitely slower going than the 50s and 60s had been. One thing researchers had to do was get creative with their projects. They worked on the same propellant molecules, but showed that these molecules had other uses as well. Carl Christie's research program went this direction. He's now a professor at the University of Southern California. Emil hired Carl at Rocketdyne in 1967, and Carl spent almost 3 decades there working with halogen compounds. Later, at the Air Force Rocket Propulsion Lab, he made polynitrogen molecules. He did a lot of really wild chemistry, probably as much as Fred or Emil. Early in his career, it was halogen compounds like chlorofluorocompounds under Emil. Later, he was the first to make stable polynitrogen compounds, including pentazenium, a 5-nitrogen cation.
That sounds like a lot of nitrogens.
Yeah, which makes it super energetic. Nitrogen-containing compounds are popular propellants and explosives because the conversion of nitrogen-nitrogen single bonds in these molecules to nitrogen-nitrogen triple bonds in molecular nitrogen gas is incredibly exothermic. In pentazenium, resonance structures make the molecule more stable than it might seem at first glance, which makes it a useful propellant. Still, even though he was able to work his way towards such an interesting new molecule, Carl is very aware that the conditions of propellant chemistry had changed. He was at Rocketdyne when winter arrived for rocket chemistry.
I mean, you cannot get any support after the Apollo program. There was zero money for new rocket propellants.
To give you a sense of how sad this period must have been for chemists, Carl rattled off a list of exotic chemicals that were unceremoniously destroyed at the Air Force's Rocket Propulsion Lab, where he worked for a decade after Rocketdyne, because no one was going to use them. 10,000 pounds of pentaborane set on fire with bullets fired into the tanks. They destroyed all their chlorine trifluoride too, and apparently the world's supply of oxygen difluoride as well.
So it gives you a good idea, that people are not going to use it very much anymore.
Cost was a factor here, according to Carl. The Apollo program proved you could get to the moon on a combination of hydrogen, oxygen, and jet fuel, all of which are cheaper than those exotic chemicals. And actually, hydrogen is pretty expensive too, so these days rockets like the Russian Soyuz and SpaceX's Falcon 9 just use oxygen and jet fuel.
And so you mentioned Carl had to get creative to keep working on propellants? How did he do that?
Carl's nitrogen and fluorine research program at Rocketdyne survived because his team transitioned to chemical lasers. These basically convert the chemical energy of a propellant into laser light. The lasers were meant to fly on huge jets or ride on trucks and shoot down incoming missiles. Other rocket chemists of Carl's generation had similar stories.
Okay, so rocket propellant research continued, although slowly. So what are we using today, besides the liquid hydrogen and oxygen that launched that satellite you mentioned earlier?
That combination does work well for some civilian rockets, but organizations around the world do use other propellants. One common fuel today is unsymmetrical dimethylhydrazine, or UDMH, sometimes in combination with regular hydrazine. Hydrazine is two nitrogens bound to one another with two hydrogens on each. UDMH replaces the two hydrogens on one nitrogen with methyl groups. The mixture is often just called hydrazine. The Russian Proton rocket and the American Delta rocket, used to launch satellites, both use hydrazine. Hydrazine combustion is extremely exothermic and can launch these big rockets into orbit when paired with oxidizers such as liquid oxygen or nitric acid. It's cheap and fairly straightforward as a fuel, but the trade-off is it's toxic. Hydrazine is also used by itself sometimes with an alumina-iridium catalyst as a propellant for the tiny rockets that adjust the position of satellites or spacecraft.
Okay, so we've got carbon, hydrogen, oxygen, and now nitrogen in our inventory, but I was kind of expecting a little more variety. Is the argument against more exotic fuels just cost and performance, basically?
There is one more thing, and this one seemed like it really annoyed some of the rocket scientists I spoke with. I'm going to call this category health and safety, both for the people handling rockets and propellants and for people and the environment where rockets are fired. To be clear, the chemists I talked to are definitely not against making propellants safe to handle. Far from it. There are a lot of stories like Fred's about things going wrong where no one gets seriously hurt, but there were tragedies as well, and no one I spoke to was even close to being cavalier about personal safety. The frustration I heard was about environmental regulations. Several scientists told me that was the difference between lagging propellant research in the US and more active programs in countries like Russia and China. Thomas Klopotky researches new propellants, explosives, and pyrotechnics at Ludwig Maximilian University of Munich. He's from a later generation than Carl's, getting started in the late 1980s. Tom isn't as skeptical about environmental regulations as some of the chemists I talked to, but he did a good job explaining the hazards of rocket launches and why the organizations that fund propellant research, like NASA or the military, care. He used ammonium perchlorate as an example. It's a popular oxidizer in solid rocket fuels. It's also a thyroid toxin, and when it combusts, it releases another hazardous chemical, HCl. Pollutants like these can accumulate at launch sites like Cape Canaveral in the US and the Guiana Launch Center in French Guiana.
Those launch facilities are stationary, and the rockets get launched again and again from the same launch site, and so you do pollute the environment with, say, HCl, which also finds its way into the higher atmosphere and forms chlorine radicals and ozone depletion.
And even though pollution is probably not a huge concern when rockets are fired in a war, Tom points out that the military launches a lot of rockets during peacetime for training. That pollution is happening on the country's home soil, and it costs a lot of time and money to clean the corrosive byproducts of propellant combustion, like HCl, off the equipment used to fire rockets.
Okay, so we've established why propellants can be bad for the environment and bad for the health of people handling them regularly, but it sounds like some scientists believe that environmental issues are kind of strangling rocket chemistry.
And in some ways, I think they're right. Those concerns definitely helped put an end to the heady, exploratory, maybe freewheeling world of rocket chemistry that Fred and Emil experienced. But while endless resources and a lack of constraints can inspire a lot of creativity and a lot of progress, I think there's a counter-argument that restrictions, while they can be frustrating, can also spur innovation.
Well, have they?
I think there's evidence that they have. This past June, NASA launched a satellite with a so-called green propellant made by the Air Force Research Lab. You remember the folks who gave Fred Hawthorne an actual ton of decaborane? That same place. The satellite carried an ionic liquid-based propellant. Ionic liquids are salts with low melting points, meaning many are liquid around room temperature. Just salt, no problematic solvents to deal with. And unlike hydrazine and other organics, many ionic liquids aren't volatile. So people handling them wouldn't necessarily have to wear respirators, for instance.
And do these ionic liquids work?
Good question. I spoke to Adam Brand, who leads propellant development at the Air Force Research Lab. He said that in addition to the safety advantages and the environmental advantages, ionic liquids have 40 to 50% more energy than the same volume of hydrazine. Ionic liquids are made of an anion and a cation. So if you have a cation that's a fuel and an anion that's an oxidizer, well then you've got yourself a propellant. Another bonus is if your ionic liquid consists of a fuel ion and an oxidizer ion, you can keep those separate and mix them just before launch. That reduces the chance of an accidental explosion during storage or transport.
Always a plus.
Yeah, and according to their proponents, ionic liquids aren't just safer, they're more versatile. Robin Rogers is a chemist at the University of Alabama who collaborated with the Air Force Research Lab years ago with Adam's predecessor, Tom Hawkins. In the time since, Robin founded a company to commercialize ionic liquid technologies for use in rockets and a whole range of other areas. Robin says an ionic liquid propellant doesn't necessarily need to contain both the fuel and the oxidizer. Remember hypergolic propellants, the kind that ignite as soon as the fuel and oxidizer touch? You couldn't store an ionic liquid if the anion-cation combination was hypergolic. But if you found a hypergolic ion you wanted to use as a fuel, you could pick the second ion in the salt to give you other properties you might want, like a lower or higher melting point, and then burn that ionic liquid fuel with a different oxidizer.
So once you have a hypergolic ion, which is a trigger ion, then you can pair it with a counter ion to improve the properties. You could design these by picking and choosing different ions.
And Robin's group even came back to boron.
Oh yeah, Fred's bread and butter.
Exactly. Fred's decaborane isn't hypergolic, but Robin says they found that if you take one boron out of decaborane, the resulting B9H14 ion is hypergolic. So they incorporated that into ionic liquid propellants. And he says they continued that work with other known propellant molecules, finding ions they could use as salts. Adam at the Air Force Lab says ionic liquids have been the focus of a lot of propellant research around the world in the last decade. The propellant on his lab satellite was a hydroxyl ammonium nitrate salt. Japanese researchers have tested that propellant as well. Sweden and China have experimented with ammonium dinitrate salts. And ionic liquids aren't the only new kids on the block. Robin has also been involved with another new type of propellant, metal organic frameworks.
Oh, MOFs. They're everywhere these days.
It sure feels like it. Do you want to explain what they are?
Sure. MOFs are solid materials made up of metal centers connected by organic linker molecules. They form these elaborate porous structures, and they're being investigated for a bunch of applications like gas storage and sensing. The very first episode of Stereochemistry was actually about MOFs, and if you haven't heard it yet, you can go check it out right after this episode.
And Robin says as propellants, MOFs offer the same advantages of modularity as ionic liquids. You can change the metal or modify the ligands to finely tune the properties. Robin worked on MOF propellants with a professor at McGill University, Tomislav Frizik. They started with a kind of MOF made with zinc and imidazolium linkers. Imidazolium is a 5-membered carbon and nitrogen ring, and that's a class of molecules known to be energetic. One of Tomislav's former PhD students, Christina Motillo, explains what happened next.
We asked ourselves if we can make MOFs also hypergolic. And what we realized was that by simply modifying one portion, so the organic portion of the MOF, we can impart hypergolicity.
Christina says the first time they tested this new MOF by putting a droplet of oxidizing nitric acid onto it, the impressive poof told them they were onto something. After graduating, Christina spun off a company to commercialize MOFs and MOF propellants.
I have a question.
Shoot.
MOFs are known for having a lot of empty space, which is why they can be useful for things like gas storage. But we've already heard that you want propellants to be dense. So how do MOF propellants deal with that?
That is a great question, and it's one I asked Christina. She said that one thing they've thought about is maybe filling that empty space with something useful, a fuel or additive that could increase performance. Christina also said that right now, they're not thinking of MOFs just as standalone fuels. Instead, they've been working with industrial partners to test their MOFs as additives that could increase the performance of other propellants. But they've shown that with the right linkers, they can make MOFs with more energy density than hydrazine rocket fuel.
So there's a lot of possibilities to explore with MOFs. Are there any other advantages to using MOFs in rockets?
Christina says the stability of MOFs makes them safe and easy to handle relative to conventional propellants. Unfortunately, compared to ionic liquids, they don't have quite the same green credentials. MOFs obviously contain metals, it's in the name, and those metals end up in rocket exhaust and get into the environment.
You know, when you started talking about ionic liquids and MOFs, you were talking about them as a response to safety and environmental standards. But now you're saying they could also be pollutants?
It's true. And in the 90s, when Adam's lab and Robin started working on ionic liquids, health and environmental concerns were very present in the rocket world. But I think something might be changing. Scientists and the organizations that use rockets are still definitely thinking more about health and safety and the environment than they did in the past. But the geopolitical landscape has been changing, and some of the old drivers of propellant research, making rockets go faster, farther, and carry more weight, are re-emerging. Al Stern spoke with me about this. He's a chemist with the Navy at Indian Head, where they research energetic materials. In terms of rockets, that means mostly solid propellants, because those are more useful in military applications. As we've heard, the space race and the Cold War meant a lot of funding for rocket research and a lot of discoveries.
And then world events changed. We focused more on, terrorist states. And then recently there's been a resurgence of the adversarial countries really kind of returning to a Cold War state. And as a result, we're sort of focusing back to that area, try to increase the range and speed of our current systems.
Al has been with the Navy for almost 30 years. When I talked to him, I also talked to his colleague, Hannah Moody, who's been working with propellants for about 5 years. One thing that was really interesting to hear was she said when she first started, they sat her down with senior rocket scientists, even retired ones, and had her read papers and books from the old days to catch her up on what rocket chemists had already tried.
I would spend my entire career only relearning what they did, but now we're also trying to push forward with new technology.
Which made me think this podcast would probably be a lot better if Hannah was in charge instead of me. Nevertheless, one of the areas of new technology Hannah talked about is machine learning. After almost 6 months of reporting this podcast, this was the first time I'd heard rocket chemists talk about artificial intelligence.
And you write quite a bit about AI.
I do. And when I thought about it, AI actually makes a lot of sense in rocket chemistry. Theoretical chemistry has been a part of rocket chemistry for a long time. Even going back to Fred and Emil's time, chemists would try to calculate the properties of different propellant molecules before they made them, which took a long time by hand or even on early computers. Theoretical chemistry has come a long way since then, which has probably saved rocket chemists time and maybe kept them safer. But Al points out that there are limitations. A good propellant balances kinetics and thermodynamics. Al says calculations can tell you the thermodynamic properties of a propellant, but there are too many variables in a burning rocket motor to accurately model the kinetics. This is something AI can be really good for, finding patterns in complex data that might be invisible to people or other methods. And Indian Head, along with other labs in the military's 3 branches, is now collecting tons of data about propellants, from how they burn all the way back to the humidity on the day they were made.
And then all of that is going to be fed to a database and see if we can use that to predict some propellant properties that right now are a little bit more, I don't want to say trial and error, but we're dealing a lot with experience and intuition on how a thing has worked so far.
So right now we're really focusing on that aspect and seeing where we can go with AI and ML and see if we can learn something that we missed.
Sounds like rocket chemistry is back.
Yeah, and not just in the US. Today, Russia and China are 2 of those competitor countries that Al referred to. And a lot of the chemists I talked to said that China, in particular, is putting much more money into rocket propellant research right now than the US is. Now, what makes this tricky is that rocket chemistry has always been a national security concern. From Fred to Hannah, all of these scientists were working on chemistry that could be used to make weapons. A lot of my conversations, even with older chemists, veered into areas they couldn't talk about because information is classified. It was even harder finding out about propellant research in other countries, which actually makes it really hard for rocket chemists to collaborate and share information across borders in the same way most chemists can. As for me, I didn't find any Russian or Chinese scientists who could talk to me about rocket propellants. I did talk to Jim Short, who's editor-in-chief of the Journal of Energetic Materials. Jim says in the 70s, 80s, and 90s, he watched Chinese researchers recreate a lot of the same energetic materials chemistry American scientists had done a couple decades earlier. Today, Chinese researchers appear to be on the cutting edge. They're coming up with ionic liquid propellants and finding ways to use perovskites, a type of crystal, to enhance rocket performance. There are 2 major energetic materials conferences happening in China just in the next couple months. So while I can't say much about the specifics of rocket research in China, I can say that it feels like China is currently leading the world's rocket chemistry efforts.
I guess that's fitting. This all has its roots in China's gunpowder rockets, after all.
Exactly.
I can't believe I've never heard any of this stuff before. I've watched a few rocket launches, but I've never put much thought into what's going on inside them.
I know, me neither, which is so crazy to me now. Propellant chemistry has some of the most interesting molecules I've ever seen. But maybe because the work was often classified, or because of the drop-off in funding and enthusiasm after the 60s, or because of rocket chemistry's association with weapons, people just don't seem to talk about it. And even though Fred Hawthorne and Robin Rogers are well-known chemists these days, their work on rockets mostly flies under the radar. Ultimately, this chemistry is what put people on the moon and sent spacecraft to Mars, Saturn, and beyond. It opened up a whole new world for us to explore. And even the dead ends of rocket chemistry are fascinating, especially the ones that propelled other areas of chemistry forward. I'm glad we get to give these stories a boost.
You and your rocket puns. Well, Sam, this was a blast. You really ignited my interest in rocket chemistry. We have soared to new heights with this episode.
Okay, I get it. Enough with the rocket puns. But next time you watch a rocket blast off, I hope you'll remember the chemistry.
Stereochemistry will be back with another episode next month. You can subscribe on Apple Podcasts, Google Play, and Spotify. Stereochemistry is a production of CNN, the news magazine of the American Chemical Society. This episode was written by Sam Lemonick and produced by me, Carrie Jansen, who was edited by Matt Davenport, Lauren Wolfe, and Bibiana Campos-Sejo. Sabrina Ashwell is our copy editor. The rocket launch sound effect in this episode was created using audio clips from NASA. The music you heard during our promo was Plain Loafer by Kevin MacLeod, and the music you're hearing now is Leaving Earth by Stanley Gurvich.
Thanks for listening.